I've been teaching college students for about 30 years. When I've asked my advanced undergraduates what they struggle with most, the consistent answer's been color. On the one hand, that's a bit odd. Color's something we've all thought about, made decisions about, when we decide what we're going to wear, or what color to paint a wall, or the whole house. And when we buy things, cars, furniture, sheets, and the like, we make plenty of choices about color. But I also understand why it's challenging. There's a difference between liking a color and using a color in a painting. Earlier, we learned that value functions in myriad ways. It creates mood, establishes compositional relationships by creating a focal hierarchy, establishes edges and creates shapes, creates the illusion of depth of space through atmospheric perspective, asserts an overall pattern, and creates the illusion of volume by simulating the effects of light on form. So value's complex, but value can only be lighter or darker. It plays out linearly on a single axis. Color's more complicated yet. It plays along three axes simultaneously. Like value, a color can be lighter or darker. So color has value. But it can also be redder, greener, or yellower. That's hue. And it can be more saturated, purer, or less saturated, grayer. So the number of possible colors dwarfs the number of possible values exponentially. And that exponential number of possible colors and the exponentially greater number of color relationships could seem overwhelming. That many of our paints are brightly colored, very nameable hues, reds, yellow, greens, etc., in one sense adds to the difficulty. Look at me here in the studio and look around you wherever you happen to be. Very little of what we see around us corresponds to the kind of color we'll be squeezing out onto our palettes. Now, I should add, it hasn't always been this extreme. For most of history, artists lived in something of a Henry Ford world. He who famously said of the Model T, you could have it in any color you wanted, so long as it was black. For tens of thousands of years, artists had a mere handful of permanent colors to choose from. Pretty much the colors we started with, black, white, and the earth tones. In the book, Art in the Making, Rembrandt, there's a chapter titled Rembrandt's Palette. Even though, as the authors tell us, 17th century Holland was something of a center for the manufacture of artist pigments on an industrial scale, Rembrandt had a limited selection. Black, white, the earths, and by contemporary standards, a couple semi-vibrant yellows, reds, and blues. Vermeer, a near contemporary, had a similarly small group of pigments to choose from. But the science of color chemistry grew by leaps and bounds in the 18th and 19th centuries. New, bright, and saturated pigments were invented and synthesized, making the Impressionist palette possible. Today, as we've noted, many companies offer over 100 different colors, with an increasing number offering over 150. The choices are pretty unlimited, so there's quite a bit to sort out. Let's start with some vocabulary. As we've noted, color has three principal attributes: hue, saturation, and value. Hue is associated with the color's name, like yellow, red, or blue. Saturation refers to a color's purity. Any of our colors could be fully saturated or less than fully saturated along a continuum ending at a dull gray. Value, as you know, refers to a color's lightness or darkness. Any color, at least in theory, can be made lighter or darker. We also refer to color in terms of temperature. As we've noted, warm colors are the ones associated with heat or fire, yellows, oranges, and reds. Cools are associated with water or a forest, greens, blues, and violets. But we can also use a term adjectively to further describe a color's character. A yellow toward the green could be described as a cool yellow, one toward the orange, a warm yellow. Mixing white with any color produces a lighter value, called a tint. Mixing black with any color produces a darker value, a shade. Mixing gray with a color creates a tone. And the addition of white, black, or gray will also diminish a color's saturation. People have been thinking and writing about color for a very long time. We could refer to this collective patrimony as color theory. Going back over 2,000 years to about 350 BCE, Aristotle writes about rainbows in Book 3 of his Meteorology. He goes off on a bit of a tangent and speculates on what artists might need as primary colors. He writes, "No mixing will give red, green, or allergon." That would be a blue-violet. He continues, "These are almost the only colors which painters cannot manufacture." The question behind Aristotle's speculation could be put like this. What set of basic colors can be used to create all the others? A full spectrum. And this has been a recurrent question over millennia. The answer has often assumed a triad. In 1810, the German poet Goethe singled out yellow, red, and blue in his seminal book, Zur Farbenlehre, or Theory of Colors. The Scottish physicist David Brewster, who rose to popular fame in 1815 for his invention of the kaleidoscope, was instrumental in codifying and promulgating the same set of three. These colors, yellow, red, and blue, are often referred to as the historical primaries. They continue to be presented as the primaries in most art schools to this day. The 19th century also saw the emergence of the contrasting young Helmholtz primaries, based on trichromatic color vision theory. This theory postulated three types of cone photoreceptors in the eye, one for green, another for red, and another for blue, echoing Aristotle. In 1931, the International Commission on Illumination, or CIE, a scientific body, agreed, defining green, red, and blue as the primaries. 20th century printing enshrined yellow, magenta, a violet-leaning red, and cyan, a green-leaning blue, as the three primaries. These, most often along with black, are what you'll find in your home color printer. The idea here is that, mixed with the white of the page, you can produce a broad range of color with these four inks. Though some professional printers use 6 colors, adding orange and green to get a fuller range or gamut. So to sum up, Aristotle says green, red, blue, violet. Goethe, yellow, red, blue. Brewster, yellow, red, blue. Young Helmholtz, green, red, blue. The CIE, green, red, blue. And the printing industry, yellow, red, magenta, blue, cyan. There have been many others who've chimed in over the centuries, but this brief sketch demonstrates some consensus. Some kind of red and blue have been repeatedly championed as primary, and then a yellow or a green. So who's right? The green, red, blue, or the yellow, red, blue contingent? Well, here we have to make a crucial distinction. Colored pigment and colored light behave differently. Let's take colored pigments in paint first. Here the historical primaries, yellow, red, and blue, seem to make sense. Mix any two primaries, you get a secondary. Yellow and blue, green. Blue and red, violet. Red and yellow, orange. Mix them all together, you get darkish mud. On the other hand, looking at light, the young Helmholtz primaries, green, red, and blue, seem to make sense. Mix blue and red, you get a violet. Blue and green, a blue-green. Mix green and red, you get yellow. And mix all three, you approach white. Light's subject to what's termed additive mixing. Paint and pigment, broadly speaking, to what's termed subtractive mixing. We experience additive mixing every time we look at one of the ubiquitous screens that surround us. In the simplest terms, all the different colors we see are varying emissions of red, green, and blue light in different ratios and intensities. This is what's referred to as RGB, red, green, blue color. When we look at paint, and indeed the physical world around us, we're primarily experiencing subtractive color. Here's the idea. When white light hits an object, say a red wall, all the other colors are absorbed or subtracted, and red's reflected. And this explains why when I mix my three primaries together, I get darkish mud, something approaching black, because a lot's being absorbed or subtracted, little's reflected back. The reason why we don't get blacks because no group of 3 or even 6 or 7 tubes covers the full spectrum. While we've subtracted a lot of the saturated radiant color, some limited parts of the spectrum are reflected back. Given all this, it's a bit ironic that you're watching electron color, paint, and pigments, subtractive color, on a screen, an additive color device. In any event in painting, we concern ourselves with subtractive color, the yellow, red, blue triad, and their secondaries. And this abstraction, 6 hues or color sensations, is conceptually very useful. These 6 can, in fact, be used to describe just about any of the scores of colors you can name. Amber, saffron, eggshell, khaki, and gold are all yellow-orange variants. Emerald, lime, and moss are greens. Fuchsia, rose, maroon, and mahogany all share red, though some list to the violet and others to the orange. We often arrange the 6 primaries and secondaries in a wheel, the color wheel. The first was published by Isaac Newton in his 1704 book, Optics. You may remember from high school physics, he placed a prism by his window and noted that the light rays traveling through the prism broke into a spectrum that projected on his room's far wall. He counted 7 colors, our 6 primaries and secondaries, plus indigo. The color wheel's often positioned with yellow in the 12 o'clock position, similar to Newton's original. In this orientation, the wheel breaks along a diagonal, upper right to lower left. Warms to the left, these colors all contain yellow and are red. Cools to the right, all contain blue. Colors that abut one another are termed adjacent or analogous. Analogous colors share a hue. Blue and green share blue, orange and yellow share yellow. So analogous colors, by definition, have a degree of similarity, and so a limited level of contrast of hue. We can mix analogous hues incrementally. Mixing yellow and green gives us a yellow-green, red with violet, a red-violet. So from the 6-color wheel, we could create a 12-color version. You'll also note in this example that we're getting darker shades of each color out toward the periphery and lighter tints toward the center. And this hints at another principle of color theory. By creating various admixtures of the 3 primaries and black and white, you can, at least in theory, create any color you could imagine. And we don't have to limit ourselves to 12 stops along the wheel. Mix yellow with a yellow-green to get a yellow-yellow-green. Mix red-violet with red, you get a red-red-violet. Doing this creates intermediate colors that share yet more with their neighbors, colors that are more similar yet, and you'd get a 24-color wheel. As we add more transitional colors, the visual path around the wheel becomes smoother, more legato, less staccato. In a wheel like this, with 72 stops along the way, the distinct colors become so similar that they begin to create the illusion of a continuous gradation. And this illustrates a key principle when using color, one that seems obvious, but one that many beginners ignore. When you want 2 or more things to be somewhat similar, clouds in a sky, walls in a room, the arms and legs of a figure, use close colors, colors that share attributes like hue, value, and level of saturation. The opposite of the sharing or analogous colors are those facing each other across the wheel. They're termed opposite or complementary colors. There are 3 primary secondary complementary pairs: yellow and violet, blue and orange, green and red. Complements share no hue. There's no yellow and violet, no violet and yellow, no orange and blue, no blue and orange, no red and green, no green and red. There are most dissimilar pairs, so they offer the greatest opportunity for contrast of hue. Mixing complements radically lowers the saturation of both. Another way of saying this is that by mixing the 3 primaries together, you diminish the saturation of all 3. Why? Because in one sense, mixing yellow and violet is like mixing yellow with blue and red, because at least in theory, violet's conceived of as a blue-red mix. By the same token, mixing blue and orange is like mixing blue with yellow and red. And mixing red and green is like mixing red with blue and yellow. As we've seen, when we mix red, blue, and yellow, we're making a color that will subtract a lot of our primary and secondary color sensations. The red subtracts or absorbs the blue and yellow parts of the spectrum, the blue subtracts the red and yellow, and the yellow subtracts the red and blue. That's the theory anyway. But while color theory is useful, it doesn't always reflect how things work with paint. First off, we don't have three primaries, in ideal red, yellow, and blue. We have specific reds, yellows, and blues. Take red. There are three cadmiums, a light, medium, and deep. The light's not a tint of the medium. It's not lighter because they added white. The deep's not a shade. It's not darker because they added black. They're different pigments, synthesized differently in the lab, and they each behave differently. And there are many other reds, quinacridone, naphthol, alizarin, and many more. Not to forget the earth reds like burnt sienna or Mars red. Theory suggests that you can mix the full spectrum using red, yellow, blue, black, and white. But you can't make a cadmium deep by mixing cadmium medium with yellow, blue, black, or white. Much less make a quinacridone, naphthol, or alizarin red by mixing any one of the cads with other primaries, black and white. Each of the pigments we use has its own personality, behaves differently. The results don't always match what theory would predict. Mix quinacridone and ultramarine, you get violet. Use cadmium, you get a brownish tone. Some reds are bluish, some orangey. Some blues are reddish, some greener. Our tube colors generally lean in one direction or another, and some are more saturated, like quinacridone, some less so, like burnt sienna. Mix cad red with its complement green, here viridian, and as theory would predict, we get something pretty neutral. Add some white, looks pretty gray. But mix red, quinacridone, a violet-leaning red, with phthalo green, a blue-leaning green, and you get violet. Here's another. Mix cadmium yellow and ivory black. You don't get a dark yellow shade, you get green. So, pigments have complex identities. They have a preponderance of something like redness, but often share aspects of other hues. A red can lean toward the orange, warmer, or to the violet, cooler. Adding to the confusion, some companies actually label colors primary blue, primary red, and primary yellow, but there's nothing particularly primary about any of them. Blick, Daler-Rowney, Sennelier, and Winsor-Newton all offer a quote-unquote primary blue. Last I looked, it's PB15, phthalo blue. That's a green-leaning blue. Lefranc-Bourgeois and Sennelier offer primary red. This is often nothing more than PV19, quinacridone violet. And primary yellow can be a grab bag of PY1, Hansa yellow, that's Sennelier, PY3, Hansa yellow 10G, that's Lucas, PY83, diarylide yellow, HR, that's Mimeri, PY97, diarylide yellow, FGL, again Mimeri, and PY154, benzimidazolone yellow 154, that's Blocks. Keep in mind where all our colors come from. All pigments are essentially either naturally occurring or synthetic chemical compounds. Ultramarine blue was first derived from the semi-precious stone lapis lazuli. Starting in the early 19th century, it began to be made synthetically in the lab. Take some anhydrous sodium sulfate or sodium carbonate, mix it with charcoal, clay, rosin, silica, and sulfur, slowly roast the mixture. First it'll turn green, PG24, ultramarine green. Keep cooking, it turns to blue, PB29. So here, green isn't made by mixing blue and yellow, it's made by heating some ingredients for a set amount of time. And blue, by theory, a primary color, is in one sense made from green, a secondary color, PG24. This same process can produce a red or violet, just vary the proportions of the ingredients, the temperature, and the cooking time. And cadmium orange is not made by mixing red and yellow, it's PO20, pigment orange 20, cadmium selenosulfide, synthesized in a lab. And our natural earth colors aren't made by mixing red, yellow, and blue with black and white, as theory would have it. As you will remember, these pigments come from rocks, inorganic minerals, iron oxide. Near black browns from magnetite, browns, reds, and orange earths from hematite, and yellows from limonite. So theory suggests you can mix the full color spectrum from 5 colors, a mythical red, yellow, blue, black, and white. And indeed, with any red, yellow, blue, black, and white, you can mix a great range of color. But the specific red, yellow, blue, black, and white you choose will make some things possible and others impossible. That's one reason why we're using a palette of 15 to 16 tubes, not 5. There's also this. Whenever you mix pigments, you diminish saturation. Mixing cad red and yellow gives you an orange, but it's less saturated than either the red or yellow you started with. It's browner, and the mix will never have the saturation of a straight-up cad orange. And the greater the number of pigments you mix together, the easier it is to wind up with mud, because each new color in a mix subtracts or absorbs more of the spectrum. That's not to say that artists need dozens of tubes to keep their color looking clean and vibrant. In practice, many artists use color selectively, using a limited number of tubes for a given painting, what we call a limited palette. We'll speak about this soon. But the palette rarely boils down to the 3 primaries in black and white. How do we know? Well, over the past several decades, technical art historians, the scientists working in museum laboratories, have done extensive work analyzing the works of many great artists. From what I've read, I'd be hard-pressed to cite any important artists who painted with this kind of palette over the course of their career. Earlier, we looked at Newton's 1704 color wheel. Over the ensuing centuries, many others adapted the wheel as a means to explain color in a range of fields, from art to science to psychology and beyond. Many examples are in and of themselves quite beautiful. We'll be painting some color charts of our own, so let's take a brief look across history. I think you'll find these inspiring, and perhaps suggest some color study projects of your own. This is from Moses Harris' 1766 Natural System of Colors. Here we also get value variance of each color, darker toward the center, lighter toward the outer rings. In contemporary usage, as we saw earlier, it's more common to find the inverse, darker values on the outer rings, lighter ones toward the center. Philip Otto Runge imagines a color wheel in 3D in his 1810 Die Farbenkugel, or color sphere, and Itten published this one in 1921. As we've seen, color theory can only tell us so much about what to expect when mixing actual paint. So it makes sense to get to know each of our tube colors individually, get to know their personalities, how they behave. That's one of the reasons artists have painted so many complex color wheels. It's a great way to explore how different mixes affect hue, value, and saturation. And while we can learn a lot about mixing color by making paintings, we can really learn a lot more rapidly by following in the footsteps of these color pioneers and explore what our tubes will do in this focused way. Artists haven't limited themselves to wheels. They've also painted many types of charts to explore color, like the 19th century French Lecoutre, here exploring green-blue in various values and saturations. And this one may surprise you. Milton Bradley, he of board game fame. In 1895, he published a book on color titled Elementary Color. While most of the illustrations were black and white, they went to the expense of including one page in full color. So let's adapt this historical practice of studying color to our own set of tubes right now. Here's what I'd like you to do. Cut a piece of canvas 9 by 18 inches. Rule a 1-inch margin around the border. Then rule a 1-inch grid in the internal rectangle. This will give you 16 units across and 7 down. If you're not using flake, you can make this an inch smaller in either direction. Paint a swatch of each of your 15 or 16 colors in the top row. You'll find the order listed in the guidebook. In this chart, our goal is to test our first color, dioxazine purple. Leave the square that's directly under the dioxazine in the second row blank. In the third row, make a lighter version by adding flake, if you're using it. In the fourth, a mix of dioxazine and titanium. In the fifth, for the primaries and secondaries, mix that mixture with the complementary earth if the color's cool, the related earth if it's warm. Here we're testing dioxazine purple, so the complementary earth's yellow ochre. You'd also use yellow ochre if the color you were testing were a yellow. You'd use raw sienna, the orange earth, if you were testing a blue or an orange, burnt sienna, the red earth, if you were testing a green or red. For the earth colors in black and white, you could skip this step, or use the space to test something else. In the sixth row, I'll add burnt umber to the mix. In the final row, mix dioxazine with black and white. To start out, I'd suggest mixing the colors in equal proportions. This will heighten your awareness of the tinting strength of each color. You can vary it as you go. In the second column, directly under the ultramarine blue, paint a mix of ultramarine and dioxazine. Then ultramarine and diox with flake. Then with titanium and dioxazine's related earth, yellow ochre, and so on. Then do the same with phthalo and on down the line. You'll find there are a couple mixes that repeat. For example, there are a couple places where you'd mix dioxazine, black, and titanium. This is a great opportunity to experiment with mixing different proportions of the colors. Looking at the chart, you'll note you have a wide range of saturations and values. This kind of practice will really help you get a handle on mixing color and also sharpen your analytic faculties in analyzing color. After completing this chart, you could do another, but this time test ultramarine blue. You'd start a new chart with ultra blue in the upper left-hand corner. The dioxazine would move down to the space after the whites. Then you'd test phthalo blue and so on until you've tested each of the colors in the top row. Do a bit every day. If you do one color a week in about 4 months, you'll have worked through your whole palette. You'll have gained a great deal of knowledge and have a visual record of each tube's mixing properties. Earlier in the course, we painted a value scale. I asked you to set it aside and said we'd come back to it later. I'd like to return to it now. In the remaining 9 rows, we'll paint a value scale of each of our complementary pairs. And in the row in between each pair, we'll paint a clean neutral based on that pair. Start with row 3. Squeeze out some cad yellow. Gauge its value. You might want to paint some on a test strip and hold it over the grayscale. The goal is to determine which gray the yellow most resembles in value. In other words, you're trying to see the yellow as if you were a black and white camera. Once you've made your determination, paint the yellow under the corresponding gray value in row 3. Now, take some white and mix it with a minute amount of yellow. The goal is to make a slightly yellowed white without materially affecting the white's value. Paint that in column 1 of the yellow row. Next, to the left of the pure yellow, mix lighter values to match the gray and burnt sienna values above. To the right of the pure yellow, we'll create darker values using a colored or chromatic black. We can make this kind of colored black using admixtures of dioxazine purple, ultramarine blue, phthalo blue, viridian green, burnt umber, and ivory black. We can adjust the mix as needed, warmer for our warmer colors like yellow, cooler for the cooler ones. Next, skip to row 5 and do the same with dioxazine purple. Now, mix the most neutral combination possible using yellow, yellow ochre, and purple. Place this in row 4 and the column according to its value. Mix all the lighter values by adding white. Mix all darker values using a chromatic black. Repeat in rows 6 through 8 for cadmium orange and blue. The neutral in row 7 will include cad orange, raw sienna, blue, white, and chromatic black as needed. Do the same in rows 9 through 11 with red and green. The neutral in row 10 will include red, burnt sienna, green, white, and chromatic black as needed. This will really help you gain greater acuity in seeing color as value, seeing your color like a black and white camera. In addition, it'll help you get to know your complementary pairs and learn to mix a range of saturations from very pure color to their chromatic gray cousins. As you work through these exercises, you'll be training your eye to recognize subtle differences of hue, saturation, and value. And this conscious effort will help you develop an intuitive sense for how your colors will behave. As Einstein famously said, intuition is nothing but the outcome of earlier intellectual experience. So you'll be able to mix a wide range of color, warm and cool, light and dark, saturated and unsaturated, and many chromatic whites, grays, and blacks. And of course, the kinds of color sensations we can achieve with paint are compounded by how we handle the paint. You'll remember this example from one of the first lectures. Each row shows 5 mixes of the same 2 colors. The first is a direct mix. The next 2 are scumbles, the final 2 glazes. The first row represents mixes of yellow ochre and raw sienna. For the scumbles and glazes, yellow ochre is the bottom layer in the first example, raw sienna in the second one. So making these kinds of experiments too can really help you discover more about color. But once we understand how to make a range of color, we have to decide what to use where. And that's just what we'll tackle in the next lecture.